Mr. Sams, what in the world are you doing up there?
Balancing on one foot.
You're pretty good at that, but I thought we were like teaching about chemistry.
We are. Equilibrium.
Equilibrium.
Yeah.
So you're equilibrating.
I am.
Oh, I get it.
Yeah.
Equilibrium, equilibrating. You are.
I keep having to adjust. As my mass shifts, I have to kind of adjust to accommodate for that.
But you know, I think in chemical equilibrium, it's a little different deal.
Close enough.
It's something else. It's like, yeah, I think you should get down so
Yeah,
you can
I'm gonna
actually
hurt
learn.
myself.
You're gonna fall down and break my podcasting.
Break your microphone? That's your biggest concern?
Well,
Thanks.
You're welcome.
I'm feeling loved today.
I'm glad you are.
Yes.
Yeah, indeed. All right, folks, we're going to do podcast 13.1. We're going to talk about
Equilibrium.
equilibrium. Yeah, so today it's equilibrium land. Hey, what is it? That's what we're going to talk about. The equilibrium constant, pressure. This is 13.1, and then 13.2 here. So got two podcasts in this particular chapter to chat about.
Go.
Hey, let's start with an analogy.
Okay.
Equilibrium. All right, boys and girls, men and women. You got the men and the women. All right. You've got the boy, and you take a girl, and you make a couple.
Yes.
That is a system of equilibrium.
It is.
Why is that a system of equilibrium?
Well, especially around here in high school land, boys hook up with girls and couples always break up.
Yeah, you see, like, boys meet girls, and then they make couples.
Yeah.
And then everything lives happily ever after, right?
Sorry.
Why are you laughing?
Because, well, we know. We observe them on a
Yeah,
daily
you
basis.
see, we've been around teenagers for probably way too long. And we've noticed that the reverse reaction sometimes occurs.
Yeah.
In fact, it probably happens at the same frequency as the forward reaction. You
Pretty
see,
close.
this is sort of a new thing to learn about in chemistry land. The double arrow. The arrow that goes forward and backwards. So we have this problem. The boys and the girls, they get together, but they also break up. The double arrow. I'm afraid we have seen this very often in our classes, actually in our school life. They break up. The boy meets the girl. They get happy, and then they get mad, and they break up. It is a reversible process.
It is.
It is always reversible. Sad, sad day. But you know it's true because it's happened to all of you, hasn't it? So sometimes when the forward reaction happens, I typically see happy, happy faces. And when the reverse reaction happens, I typically see sad face. Yes, indeed. So this is a great analogy, Mr. Sams.
It is.
To reversible reactions.
Yeah, all reactions are reversible.
No, that's not true. I would disagree. There are some reactions that are not reversible. If I take a piece of paper and I burn it, I cannot turn it back into a piece of paper with the carbon dioxide and the water and maybe a small chance. But some reactions are highly reversible and some are not very
so
reversible.
reversible.
But we're going to be talking now about reactions that are primarily reversible. All right. So we could think of it like a dance. Who's present at the dance?
Chaperones.
True. But the chaperones don't matter.
Oh, okay.
And you know, you kids who are watching this, you know the chaperones don't matter. You've got the boy, the chaperones, and you've got the girl, right? Probably should give her some arms. Boys and girls. But what happens? They collide. And of course, they make couples. And they live happily ever after until, of course, they break up and then they're not so happy.
Or the song ends.
So we could graph this,
Yeah.
all right? So let's think more chemically.
All right.
All right, if we start at the dance. Now, let's assume that nobody comes to the dance with it as a couple.
Okay.
So we'll start here with...
Called the ad hoc dance.
Yes, this number of boys. And as the dance progresses, you will have the boys diminish. You have less boys. Now, that's sort of weird to say that there were less boys.
Well, you're either a boy or you're a couple. So once you become a couple, you're not a boy anymore.
Right. And the girls, let's say for the sake of argument that more girls went to the dance, right?
Okay.
And so what's going to happen is that they're going to diminish too. But eventually, they're going to reach a point. And the number of couples that are going to happen as time progresses, blue, maybe a blue, is there'll be no couples, but as time progresses, there will be a steady number of couples. So this is the couples. Couples? And this would be the girls, and these are the boys. Okay? And so you have the couples. But actually, even though we have now reached a point. This point we would call equilibrium.
Mm-hmm.
Even though you've reached this point, it's as if a lot of people think that it's now boring. You have the same number of boys and girls and couples. But you see, this process is said to be dynamic. Hence the next slide. Actually, it's a couple of slides later. I think we've already said that. So the definition of equilibrium, this is said to be dynamic. What is the definition of equilibrium, actually, as per that graph?
That's when the rate of the forward reaction is equal to the rate of the reverse reaction. So for every couple that breaks up, another one gets formed at the same time. So it's not boring. It's not like everyone is now stuck in their coupleness or not, but the couples keep shuffling around. So you're dancing with new people and getting to meet some new friends and so on.
So dynamic means that it is constantly changing. Not the amount.
Right.
Constantly changing.
Hmm.
Like I said, the amount of people changing is not changing.
Right.
But the ones who are there are changing.
Yeah.
You see.
Kind of like you have a mainland and you have an island. And the island can only support 20 people. And there's a bridge going to the island. And cars are constantly going to the island and from the island. The number of people on the island doesn't change, but the actual people on the island do change because the cars are constantly going and coming. But there's always 20 people on the island.
Yeah. This would be like, this would be a city. And this is the island off the city, right?
Yeah.
And the cars go across in one direction probably in the morning because it's time to commute to work or whatever, and then they commute the other direction. And so the rate of the forward in a given day, let's say, is equal to the rate of the reverse reaction. So that's another good analogy. You know, another thing that we could do, let's talk about this. So folks, here's an example. I want you just to take a look at this flask, which has a stopper in it, and it is a sealed system. And so what we've got going on here, it's a dynamic equilibrium. Now, if you look at this, you would pretend you'd say it's kind of boring. It's just a flask of water, right? But if you look carefully at the flask, you will notice there's some condensation on this flask. That condensation, of course, is the water. Where did that come from? Well, you see the water evaporated. It went from the flask, from the liquid state to the gaseous state. So that is like the breaking up of the couples. Okay, and then you also have the formation of the couples. The water vapor that's in this flask is condensing, and you can see them condensing, forming. And so if this is at a state of equilibrium, which it is the rate of the forward reaction, the rate of the evaporation, is equal to the rate of the condensation. Let me write this on the screen here while you see this. So essentially this is water liquid is turning into, but double arrow here, into water gas. And this is a dynamic equilibrium happening here in the flask. Now scientists are not just happy with the reaction of saying, well, it's dynamic. We actually prefer to measure it. We love numbers. Science and math, they actually go together. Amazing. So let's take a particular reaction where we have J, A, K, B, N, C, M, D. So it's like a double replacement reaction where the J, the K, the N, and the M represent the coefficients in the balanced equation. So there's something called the K. The K value is the equilibrium constant. Now, I know you spell constant with a C, but I don't know. We use C's for other things.
Maybe it's German.
So the equilibrium constant has a particular form where you just basically it'll be the products over the reactants.
It's also called the law of mass action.
Law of mass action, which we've said up here, but I didn't actually say it. But it's called the law of mass action, where you would say the concentration, remember constant like moles per liter, of C to the power of N times the concentration of D, those are my two reactants, to the power of M, divided by the concentration of A to the power of J times the concentration of B to the power of K. And this would be a number, and it would vary depending on the concentration. So if you are at equilibrium, this should be a double arrow, Mr. Sam.
It should, you're right.
That should be a double arrow. So this is double arrow. So C, whatever the molarity is, to the N power, D to the M power on top, A and B on the bottom to their appropriate powers, J and K.
And that is equal to K.
And this is called the equilibrium constant, sometimes called Kc, or just big K.
Yep.
All right. And this is, one thing about K is it does change, and it changes only with one variable. That would be...
Temperature. Only changes if you change the temperature.
Only the temperature. Only the temperature. All right. Just...
Only changes if you change the temperature.
So if I were to change the molarity, what would happen?
Well, K doesn't change.
But I changed something.
No!
It's only the temperature. So if I change the pressure?
No.
No. If I add a catalyst?
No.
If I make it orange?
Nope.
Okay. Only with the temperature. Okay. Now, what the heck does K mean? All right. So there's three sort of varieties.
My son's learning that. He just learned K a couple days ago.
All right. K can be either greater than 1, less than 1, or just about equal to 1. When K is greater than 1, actually, if we just kind of look at it, it's a mathematical expression.
Yeah.
So if this number is bigger than 1, that means that the top number is big compared to the small number.
Right.
The bottom number. So therefore, that means you have what?
More products than reactants.
That means more products. Conversely, if we have a little number on, let's say, products over reactants,
then you have a small K, less than 1.
so that would be, I think I went the wrong direction tonight. Then that would give you a, so as K is smaller than 1, then you have more reactants. Actually, when we say more products, by the way, we also say that the reaction shifts to the right. And if it's K's left, it shifts to the left.
Or favors the forward reaction, favors the reverse reaction.
So let's say favors here. Favors the arrow to the right, and that means the forward reaction.
So we're not really shifting in this stage of the game.
Yeah, we're not shifting. It just favors one of them. Yeah. And if K is about equal to 1, we've got
about the same.
Now, that's not exactly always the same. Let me write this down so I don't try and talk and write at the same time.
It's relative to their coefficients. And
because sometimes if you've got a square in the top and a cubed in the bottom, it kind of changes things. But that's roughly true. Okay? All right. Now, we can also not just talk about the concentration. We can write an equilibrium expression that talks about pressure. Right. And actually, not just pressure, but partial pressure.
Yes.
Partial pressure. Partial. All right. I need a double arrow here. Okay.
Did you know that K only changes if you change the temperature?
Really? I didn't know that.
Yeah.
So this is actually not called the KC, but notice it's called the KP.
For
pressure. And so I take the pressure of the ammonia, the NH3. Now,
the product.
Now, as a note, the symbology of writing partial pressures is you put a capital P, and then you put the chemical, whatever it might be, X, and then, that's it.
Symbology?
Symbology, is that a word?
I don't know, but I
like it. Scientology. No, that's something different. Okay. Symbology. Symbology.
I like it.
Symbology. All right, so if I square this, why did I square that, Mr.
Because there's two coefficients. I
also
put it in parentheses too, by the way, just the way I did it.
And the ammonia is squared because of the 2. So it's basically still products over reactants.
Yes, sir.
Over the partial pressure of the nitrogen. So you do this like that?
Yeah.
Oh, okay. This would be the first power because there's a 1 in front of the nitrogen. And in front of the hydrogen. All right, everybody take your time. Think. What should I put in there? Come on, Lee. I know you know the answer to this question. That's correct. Cubit. Oh, sorry, I picked on Lee because he sometimes is a slacker. So, okay. Not
and
true.
he forgets his units.
And he forgets his units, yeah. Okay. And actually, he's already watched this podcast, so I guess for the rest of the world, you'll have to figure out who Lee is. Okay. All right. And lastly, on this podcast, we do want to say that there is a relationship between KC and KP. And that's very simply this. KP is equal to KC times RT to the power of the delta N. All right, we got to make sure we know. KP, we talked about, right?
Yep.
The pressure, constant.
Yep.
The concentration, constant. Sometimes, by the way, we can just call that K. R is the gas constant. Now, since we are talking about pressures,
which one?
Since we're let's kind of work. Typically, we like to work in atmosphere since there's a pressure thing. So I would say 0.0821. That one would be your best choice. If you use the 8.314, then you'll get your pressure in kilopascals. And the temperature must be in Kelvin degrees. Now, we do have one other thing. What the heck is delta
N? That's the change in the number of moles of gas.
Change in moles of gas. Now, let's go back to this problem right here from Mr. Sams. What would delta N be in this case?
-2.
-2. So how did you get the negative 2?
Well,
You're
if it's
correct.
a change in number of moles of gas, so on the left-hand side of the equation, we have 1 mole of nitrogen and 3 moles of hydrogen. That's a total of 4 moles of gas. That goes down to 2 moles of ammonia. That's 2 moles of gas. So we started with 4, went down to 2. That's a change of minus 2.
You went down by 2.
Yeah.
You also could think of it as products minus reactants.
Right.
2 minus 4, negative 2. So delta N in this case would be negative 2. So if you knew, let's just do this just for fun. Let's say that we knew that the Kc for this particular reaction was 22. And we were trying to find it at 400 degrees Celsius. That was true at 400 degrees Celsius. What would the Kp be?
Oh, you got to make me do math.
I know.
Well, we need a reaction. Is it the reaction we
Yeah,
just
the reaction we just did.
Okay.
So Kc is 22, which means that the products would be favored. And so I'd say 22 times RT, so this is 0.0821 times, now the temperature, we have to convert that to Celsius, or from Celsius to Kelvin, so 273, that'd be 673 Kelvin, and to the delta N. Now delta N would be to the power of negative 2, as you recall. Now remember, if you powers, you have to do this to the negative 2 power first, then multiply by 22, right, mathematically. And Mr. Sams, I think, has trustfully found the calculator answer.
It would get 4.86 times 10 to the negative 5.
And actually, this actually brings up
Oh,
an
wait, no, we
important-
don't, because I just put... Oh, okay, I screwed something up.
So Mr. Sams is wrong.
I am wrong. I hit the plus button instead of the times button
Oh
somewhere.
yeah, that's not going to work if you
Yeah, sorry about that. I
This
just
is
got
a
my mistake.
times, not a plus.
Just a moment. To the negative 2 power
Times
times 22. There we go. Now it's 7.2 times 10 to the negative third.
Now, folks, notice about this. We haven't really said this, but what are the units on K?
We don't care.
Yeah, an important thing about Ks, the capital Ks, and we're going to learn lots about capital Ks over the next actually months. It's kind of a big topic, equilibrium constants. But the unit on K, there is no unit. There technically kind of might be a unit, but since it varies, scientists do not worry about the unit on K. So here we've been talking about how important it is to have units. But guess what? In the unit, at least for the unit for K, what did I just do? The unit for K, there is no unit. No unit on K. Good with that?
I'm good with that.
Okay.
Simple.
So, any last thoughts on the boys and girls and couples, Mr. Sams?
I know one couple that dated in high school that are still together today.
Yeah. Actually, we'll talk later about, like complete dissociation.
Yeah.
What's true about all high school romances?
They all break up.
Except for your friends.
Exactly.
But
They're the one
But
exception.
you guys out there in the internet land, you know that you're not going to stay with him or her. So you be nice to him or her.
Yeah.
Okay, and don't mistreat them, so that
Exactly.
you don't have regrets and things. So friendly advice from
Be
your
nice.
chemistry teachers: be nice, be happy. Isn't there like a song? Be happy, be nice.
Don't worry.
Be happy. Yes, we have the music going. Yes, indeed. You need help, Mr. Sams. You must be balancing. Should I try the balance thing? I balance.
Ooh, don't forget you're old. And you're
I'm
gonna,
old, but
you're gonna fall.
I am good athlete.
That's true.
Surf in USA. I surf USA. All right. Bye bye.